Hello, I'm going to show you all how to solve the Weaver game in two different time complexities. Weaver is a word game similar to Wordle. Using four-letter words, you begin with a starting word and an ending word. And the goal of the game is to find a path from the start word to the end word, where each consecutive word is one letter off from the last. To solve Weaver, the first step is to gather a list of four-letter words and construct a graph. In this graph, each node is a word, and each edge connects to another word that is one letter off. The second step is to run a shortest path algorithm from the start word to the end word. This ensures that we play the game optimally, since we want to minimize the amount of words it takes to get to the end. Normally, when we think of finding the shortest path, we'll think of using a star or Dijkstra's algorithm. However, in this case, since it's an unweighted graph, breadth first search also finds the shortest path, and it happens to have a quicker worst case time complexity. A graph consists of vertices and edges, and our vertices are just represented as our list of words. However, our edges we're going to represent by using an adjacency list. An adjacency list is a list that maps vertices to a list of their neighbors. The first method I'll go over for populating the adjacency list will be a brute force algorithm that works in O of n squared time. In order to do this, we will loop through each word in the word list. Then for each of those words, we loop through the list again and compare the words to see if they're one letter off. If so, then we'll add it to our adjacency list. Since we loop n times for each of the n words, we have a time complexity of n squared. The second method for populating our adjacency list works in O of n time. To begin, we initialize a hash map that maps words to a list of words. We'll be taking advantage of the fact that get input is typically constant for hash maps. The first step is for each word, we're going to break them into four parts, where the first letter is replaced with a 1, second letter replaced with a 2, third letter replaced with a 3, and so on. Then, using our hash map, we want to get the list by using each part as a key, and we want to append to that list our original word. So in this case of our first part here, we're going to get the hash map list that corresponds to this, and what we're going to add to it is our original word, which in this case is word. And we'll do that for all four parts. Now that our hash map is populated, we can finally populate our adjacency list. To do this, we again iterate through all the words and break them each up into four parts. Now we can grab the four lists corresponding to each part, and to finish, we map the original word to the combination of those four lists. Note the lists corresponding to each of the four parts contain one copy of the original word. So then when we combine the lists to add into our adjacency lists, each word will have four copies of itself in the list. Here's a visual. We have our list of four-letter words, and we break them each up into four parts. Then we populate our hash map by appending our original word to the list stored in the hash map where each part is used as a key. So this is a key, this is a key, this is a key, and so on. Now that we have our hash map populated, we can begin to populate the adjacency list. So for each word in our word list, we again break it up into four parts. Using those four parts as our keys, we get each of the four corresponding lists from the hash map. Then we can map each original word to the combination of those four lists. And note that each list has repeating words of itself, but with them removed, it is the adjacency list. And the last thing to do is just run BFS on our graph from the start word and stop when the end word is reached. So now that we know how our program works, we can begin coding it. First thing we want to do is import numpy. We'll call it np. And we want to load our four-letter word list. We'll call it words. We'll do np.loadText and say the file is called four-letter words. We're going to say that the type is string. The word list I have happens to be in uppercase, so I'm going to switch it to lowercase. We could also pre-process this beforehand. Now let's get our start word. make sure it's all lowercase. And our n-word. Now we can pre-process our words using our hash map before creating our adjacency list. So in Python, a hash map is just a dictionary. We're going to iterate through all the words in our word list. And then we're going to go through each word and break it up into 4 parts. So for example, if we have A, B, C, D, we'll have 1 B, C, D, A, 2, C, D. So we'll go through every letter in the word and we'll break it up. So the first part will be this. So in Python, after the colon, it's not inclusive, and then before is inclusive. So in the first, so we're gonna have 0 first, and that should be a 1, right? Here is the 0th when j is 0. So that would be word of 0 plus string of 0 plus 1 plus word of 0 plus 1 colon. And that'll end up being word of 0 plus string plus word of 1 after. And this is nothing, since this is not included, then this is essentially an empty string. So, and then we have 1. Oops. And so we have now index 1 inclusive and everything afterwards. So 0, 1, and then everything after, C and D, B, C, D. So now that we have our key, which again is this, we can check, since the hash map is empty, we can't exactly grab what's in the hash map yet because it'll throw an error. So first we're going to check if the key is in the hash map or not. So if the key is not in the hash map, then we want to put it in. So we can say that hash map key is equal to a list containing just our word. And if our key is in the hash map, then we can just add on to that list. And that would be our word. Now that we've populated our hash map, we can go ahead and create our adjacency list. So first things first, let's create an adjacency list that is empty, and it's just a dictionary in Python. And we want to iterate through our words. So for word and words, and we want to initialize our adjacency list to a list that's empty. And then again, we want to go through our word and break it up into 4 parts. So I'll just copy this here. And then we want to add what we find to our adjacency list. So we're going to do plus equals, and then we're going to add what we get from our hash map. And again, this will contain 4 instances of our word after we add each part. And we're done populating our adjacency list. Now that we have our adjacency list, we can go ahead and do breadth first search. So we're going to create a dictionary that represents our distances. And the first thing we want to do is set the distance of all our vertices to infinity. I'm going to move this up here so that we can go ahead and set all those words to infinity. Then we want to set the distance of our start word to 0, since it's where we begin. Create our queue. And we want to keep track of the path that is traversed as we're going along BFS. So first things first, while the length of the queue, so while the queue is not empty, then we'll set u equal to what we pop off from the queue, so the front of the queue. And then for v in our adjacency list of u, so we can say that this connection is u to v. So we're grabbing u here, and then we're using the adjacency list. We're seeing all the v's that are connected to u. So it's u to v1, u to v2, u to v3, and so on. If v is equal to the end word, then we can set our path traversal of v to be u. And we can say that our queue is now empty, and we can break this loop. We make our queue empty so it doesn't have to search anymore. If v is not equal to u, so we need this because up here we contain 4 instances of our word, so we want to make sure that v is not equal to u, because we can't have an edge going to itself in this case of our graph. Now we want to check if our vertex has been visited by checking if it's equal to infinity. Then we want to take note of where it came from when traversing this path. So we know that we got to v from u. And then we want to append to the queue v and set the distance of v to distance of u plus 1, since it's one more edge. And that's it for breadth first search. Now that we've finished breadth first search, we can go ahead and see if our path found our end word. So we're going to go ahead and create a list of our path, and we're going to go backwards from the end word to the start word. First thing we're going to check is if our path traversal even has end word in it. If it doesn't have end word in it, then we know it's part of a completely different connected component, and so there is no path from our start word to the end word, so therefore path is not found. Now, else, we can actually begin to find our path. So we'll say next word is equal to the last word in our path travel list. And while next word exists in our path traversal, then we'll add on to our path travel what is connected to our next word. And then we'll set our next word equal to, again, the last of our path travel. And last but not least, we can print out our list. Our list is going to be backwards since we start from endward, so we can go ahead and reverse this. Now that our code's done, we can go ahead and see an example. So I have the Weaver game up here, and our start is flag and our end is poll. So we'll run our game, flag, poll, and here we get our list. So we'll do flat, plat, peat, pelt, pel. Oh, pel is not in our word list here. So this happens sometimes. Our our game is really only as good as our word list. If our word list doesn't have all the words that Weaver has, then we may not find the optimal solution. If it does have all the words Weaver has, then we will find the optimal solution. And sometimes we can have words that don't exist in Weaver, but that's all right. We can just remove it from our word list and go ahead and try again. In this case, I'm going to just switch to another one. So stay woke, sway away, awry, airy, wiry, wire, war, woke, and we win. And there are some that it doesn't work for. So, for example, if we do vote and veto, it doesn't have a path. And again, this just depends on your word list. You can have a really good word list that it works for all the Weaver words. You could have a word list that maybe isn't very well connected. I do want to note when I was creating this video, there was a few spots where I was just missing a colon, whether it was like a for statement or an if statement. I want to show you all the difference between O(n) squared algorithm time and O(n). So if we have, say, 1,000 words, our O(n) is going to be 1,000 and our O(n) squared is going to be 1,000,000. So it's a huge difference in the amount of computation that's being done. So we're going to just write out the brute force algorithm. So we can remove this hash map stuff that we don't need. This is where we create our adjacency list. So we can initialize our adjacency list, that's fun. Now we want to go again through our words. And we want to count the difference. So at first it's going to be 0. And for the 4 letters in the word, we want to say if the other word's letter is not the same as our first word's letter, then we'll add 1 to the difference count. And then after that loop is done, if our difference count is equal to 1, then we can add that word to our adjacency list. And so this is our brute force algorithm. So let's start again with the original one. I believe it was stay woke. So stay woke. Pretty quick. Now if we do the other one, stay woke. Takes a while. But that is all. Thank you very much.